Hi everyone, this is Yuxuan Cai from Northeastern University. In this video, I'm gonna present our work, YOLObile, Real-Time Object Detection on Mobile Devices, via compression and compilation co-design. Object detection has been widely used in multiple tasks, such as object tracking, segmentation, image annotation, activity detection, and so on and so forth. Based on different tasks, it is applied in different applications, such as autonomous driving, UAV obstacle avoidances, robot vision, human-computer interaction, and augmented reality. The modern object detector using convolutional neural network has made a great progress in accuracy. The DNN-based object detectors can be categorized into two mainstreams, two-stage and one-stage. Two-stage detectors divide the detection into two stages. First, extract the region of interest, which refers to ROI, using an RPN network, and then do the classification and bounding box regression tasks based on the ROI. Due to the two-stage detection procedure, such two-stage detectors are quite slow in inference speed. Even on desktop GPU, it can hardly reach the real-time requirement of 25 frames per second. One-stage detectors, such as YOLO, directly classify and regress the candidate anchor boxes from each spatial location of the feature maps. Though faster than the two-stage detector, on mobile devices the inference speeds are still quite low. There are also some lightweight object detectors, such as YOLO Tiny, MobileNet SSD, which use lightweight neural networks as backbones. Some of them can reach the requirement of real-time on mobile devices. However, the accuracy suffers severely, and this is not acceptable. To seek for solutions of increasing inference speed as well as maintaining the accuracy, we seek for model compression. A representative model compression technique is model pruning, including non-structured pruning and structured pruning. Non-structured pruning is fine-grained, prunes the arbitrary weights, and results in a sparse weight matrix. It was proposed less than 5 years ago, but have only limited use in actual development. The reason is, for the sparse matrix after pruning, it requires indices in inference process, and this will cause speed degradation mostly in CPUs and GPUs, where the hardware parallelism need to be maximized. So this is the reason people are more focusing on the so-called structured pruning. Structured weight pruning includes filter pruning and channel pruning in weight matrix. Take the convolution layer as an example. Filter pruning prunes the whole filter in 40-weight tensor, and after using general matrix multiplication to transform the tensor into 2D weight matrix format, the pruned position becomes the whole row as the right figure shows. The remaining computation is still a full weight matrix, but the size is smaller, so the hardware parallelism can still be maintained. Overall, this kind of technique is hardware friendly, but often results in accuracy loss due to the cost of granularity. In this year, a work called Pattern DNN in our group proposed pattern-based pruning. For each kernel in a convolution layer, it prunes a fixed number of weights. In other words, it assigns a pattern from a predefined pattern library. It can also remove the whole kernel, which is called connectivity pruning. Pattern-based pruning simultaneously preserves the accuracy and the hardware performance due to its flexibility, but it is only applicable to 3x3 convolution layers. Our YOLOv4 has 83% 3x3 layers. Even remove all the 3x3 weights, it can only achieve the compression rate of 5.9 times. In practice, with only 5 times compression, the MAP drops by over 20%, and this is not acceptable. So our motivation is to find a fine-grained structured pruning scheme that can simultaneously achieve high accuracy and efficiency. Also, it is applicable to all kinds of layers, 3x3, 1x1, depth-wise, point-wise, fully connected, and so on and so forth. We also need our compiler to support this structured pruning scheme and even further increase the DNN inference speed. Here we propose a compression-compilation co-design framework called YOLObile, and this is an overview of our YOLObile framework. Our framework includes 5 parts: Mobile-Unfriendly operation replacement, block-punched pruning, Reweighted pruning algorithm, compiler-assisted acceleration, and mobile GPU-CPU collaborative computing scheme. Before we compress the model, we need to replace or remove some of the mobile-unfriendly modules and operations in original YOLObile 4 network. For example, we remove the spatial attention module, which has an extra bypass convolution layer and a sigmoid activation function, because it has an exponential sigmoid activation function which can become the latency bottleneck on mobile inference process. We also changed the mesh activation function, which is also a new feature in YOLObile 4, back into liquid ReLU. It is not supported in ONNX, a format that we use to store the model structure and read on mobile devices. It brings in extra memory consumption when training on PyTorch, therefore extends the training time. The second part is block-punched pruning. To mitigate the shortcoming of structured pruning and pattern-based pruning, we propose the block-punched pruning. In one block, we prune the same weight in each filter. Also, we prune the same weight in each channel, making all the kernels in each block, like 3x3, 5x5, or 1x1, follows the same pattern. In different blocks, the pruned weight position can also be different, and the number of the pruned weights can also be different. Like in block 1, we prune 4 weights in each kernel, when in block 2 we prune 5. In our block-punched pruning, block size affects both accuracy and hardware acceleration. On the one hand, a smaller block size provides higher structure flexibility due to its finer granularity, which typically achieve higher accuracy but at the cost of reduced speed. On the other hand, larger block size can better leverage the hardware parallelism to achieve higher acceleration, but it may cause more severe accuracy loss. So how to select an appropriate block size? For the channels in each block, we make it equals to the length of the vector registers in mobile CPU and mobile GPU. This can fully utilize the mobile device's parallelism. More channels won't bring in extra performance increase, but cause accuracy drop. For number of filters, we determine it by experiments, try different block sizes, and find a Pareto optimal point of accuracy and speed. Here is an FPS versus MAP figure of different block sizes. We fix the number of channels to 4 and test different block size. Consider the trade-off between MAP and the block size. We choose a block size of 8x4 in the end. Besides parallelism, what are the other advantages, and why we use block-punched pruning? For memories, since the same locations are pruned among all the filters within each block, these filters will skip reading the same input data and mitigate the memory pressure. From the computation point of view, the location restriction across channels ensures all the channels to share the same computation indices. So when we use multi-thread to calculate among these channels, different threads can follow the same computation procedure, and we call this eliminating computational divergence. We adopt the Reweighted regularization as a pruning algorithm. The general Reweighted pruning problem is formulated as the DNN loss, which is a function of weight and bias, plus a regularization term. The only hyperparameter lambda controls the trade-off between accuracy and sparsity. Using our block-punched pruning and unfold the weight W into small blocks, we can calculate the regularization term. We denote it as the L2 norm of penalty alpha, element-wise multiply by the weight value, W. And for penalty alpha, on iteration t, the alpha t is the reciprocal of the square of L2 norm of the weight in iteration t minus 1 plus a small value, so this alpha is a constant. The regularization term punishes the small magnitude weights, and the large magnitude weights are kept. After 3 to 4 iterations, we will prune the weights that converges to 0 and retrain the non-zero weights to regain accuracy. After block-punched pruning, our framework relies on a compiler-assisted acceleration framework to achieve the efficient increase on mobile devices. The compiler is based on work called PatentDNN from our group early this year. We use a more efficient storage format called block-punched compressed storage format to store the weight. And our framework introduces a matrix reorder optimization to group the weights with the same computation patterns together. In addition, our framework generates both CPU and GPU codes for each layer and codes the appropriate one according to our mobile GPU-CPU collaborative computing scheme during the actual inference process. Now let me introduce the GPU-CPU collaborative computing scheme. Now let me introduce the mobile GPU-CPU collaborative computing scheme. We know that GPU is suitable for the convolutional computing, but in non-conv layers, GPU can have a faster speed as CPU. For the CSP connections in YOLObile 4, we consider moving the less computational intensive branch 2 to CPU and running the 2 branch simultaneously if CPU inference latency is less than the sum of layers in branch 1. Otherwise, we run the 2 branch sequentially. There are also several layers of non-conv operations in the YOLOhide output part. We consider running them on CPU and GPU simultaneously, and we propose an offline device selection method based on 0-1 integer programming. In our experiments, we train our model using NVIDIA Docker and PyTorch 1.6, and the total training cost using 4 RTX 2080 is 4 days. We use a Samsung Galaxy S20 to test the speed on mobile devices. And our YOLObile is derived based on YOLObile 4 with 320 by 320 input images and trained on Microsoft Cocoa dataset. We denote MAP as the average position under LU 0.5 threshold and AP 0.5 to 0.95 as the average precision under LU from 0.5 to 0.95. In the evaluation result, we can see our YOLObile has only 3.95 G-flops. Number of computation, we achieve 14 times compression rate with only 8% MAP loss. And here is an accuracy and speed comparison with other object detection approaches. On the top 3 lines of the table, there are some representative one-stage object detection works. We can see they have a large amount of weights and inference at a low speed. In the middle of the table, there are some lightweight models using MobileNet or TinyDuckNet as backbones. However, the lightweight backbones cannot retain a high accuracy. By using model compression and mobile CPU-GPU collaborative computing, our work can have a comparable accuracy as the large model did, but the inference is much faster. Here is a figure of FPS versus MAP of different works, and all the results, including other object detection approaches, are evaluated under the same compiler optimizations. Our YOLObile lies in the top right of the chart, outperforms other representative reference works in both accuracy and speed. Our work provides a Pareto optimal trade-off solution that maintains both the accuracy and the speed. Here is a demo video recorded on a car park road. We can see our YOLObile successfully recognize the cars, trucks, and pedestrians. Here is a demo video recorded in Target supermarket. And here is a demo video recorded at home. In conclusion, in this work, we propose YOLObile, a real-time object detection framework on mobile devices via compression and compilation co-design. Our work includes 5 parts: Mobile-Unfriendly operation replacement, block-punched pruning, Reweighted regularization pruning algorithm, compiler-assisted acceleration, and mobile GPU-CPU collaborative computing scheme. We also do the evaluation and ablation study. For future work, the prune ratio and the compiler optimization of our work are manually designed. These processes are time-consuming, and to free us from designing hyperparameters by experiments, we are now working on network architecture search, which uses search strategy to search for an optimized network architecture. We are also working on using some strategies to automatically search the prune ratio and prune scheme, using multiple pruning schemes in the same network. We are also thinking for other efficient, fine-grained structured pruning scheme. And that's all about our work. In the end, please let me introduce CocoaPi, the world-leading real-time AI on mobile devices through compression and compilation co-design. For more demo videos, please follow our YouTube channel and Bilibili channel. Just search CocoaPi and you cannot miss it. Thanks for listening.